Welcome to module 3 of System Verilog, and we'll be discussing part 3 of this module. This session discusses about Verilog event scheduler phases. Now, when we are dealing with the Verilog program or System Verilog program, simulation events occur in 4 phases. The 4 different phases are as follows. So, first is the active region, which gets simulated, followed with inactive region, and inactive regions are those statements which are prefixed with #0. Then comes the non-blocking updates, and then the monitor finally. So for example, in this particular example, we have two data types, two datas, A and B of type logic. And in the initial block, we have all the blocking statements, which are nothing but the active region of the code. So this is active. So they simulate first. So A is 0, B is 0, A is 1, and hence A equal to 1 will be the final update in the active region, followed with the inactive region. And because it's prefixed with #0, the statement is inactive statement or inactive region statement. Then we have non-blocking updates which happen. So for example, in this case, we have A less than or equal to 0. So that's non-blocking assignment. Followed with at time 0, there are no monitor statements. But at time 1, we have one monitor statement, which is $display. So that becomes monitor statement. So let's see how they get executed here. So at each step, events are executed in 4 ordered regions, as I said. So procedural statements, that is all the blocking statements, blocking assignments, if, for, etc., and also display of the monitor. They all occupy the active region space in the queue, followed with inactive, which is #0 again, as I said. So that's a #0 delay, which says that these statements should be delayed, should be executed at the end, that is before the non-blocking assignments happen. Then we have non-blocking updates, updates from less than or equal to happen here. Then the monitor statements execute. So let's see the diagram here, which explains all these statements in detail. So we have active region, that is from the previous time slot, the simulation moves to current time slot, and in the current time slot, active region code gets executed, gets simulated. So what are the active region assignments which get simulated? They are blocking assignments, and also the RHS of non-blocking assignments happen here, that is right hand sides assignments, which are on the right hand side of the non-blocking. They they get activated here, followed with $display, as I said, which is also the monitor command. So $display also occupies the active region. Then we have continuous assignment. So these all take the place of active region. In inactive region, as I said, it's #0, which is blocking assignment. Non-blocking assignment, the LHS of non-blocking assignment update here in this region, while RHS gets updated in the active region. So this you have to take care. You have to understand this concept. Then what are the things which are postponed? That is after in non-blocking assignment, what gets simulated are $monitor, $strobe. They get simulated after all the 3 things happen. And then it goes to the next time slot. Also, you have to take care that during in the NBA region, in any changes, any update to NBAs can also trigger, re-trigger more active events. Now, what is this? Let's see in the next following slide. So this is what is the picture which you have to remember in order to analyze and understand how simulation happens, what type of order in which they get simulated. So this is the picture which will give you a clear idea about the order of simulation in System Verilog or Verilog. So for example, let's understand what happens here in this code. So we have a module which is by name schedule underscore test, and it has 2 variables, A and B. Now in the block of initial and end here, which is the block wherein we have encapsulated few codes. A is 0, B is 0, and A is equal to 1. So this entire thing, it's a blocking assignment statements. So they all come under active region. So under active region, A is equal to 0, B is equal to 0, then A is equal to 1. They all come under active region. So they execute, they simulate at time is equal to 0, right? So the final update of A will be A equal to 1 and B is equal to 0. So that is what is shown here. So time 0 in the active region, A gets equal to 0, B is assigned 0, A is again assigned 1. So the final value of A and B are A equal to 1, B is equal to 0 when this gets executed. So dollar display also happens in active region. So in active region, we also have blocking as well as dollar display. So it prints A is equal to 1 and B is equal to 0. This gets printed. This gets displayed on the monitor. Next, we have inactive region, that is hash 0, B equal to 1. So in inactive region, B becomes 1. And so now the final value of A and B till here, when we come till here, when the simulation comes till here, is A is equal to 1 and B is equal to 1, correct? So this happens in the inactive region. This happens in the inactive region. So, and then we have this non-blocking assignment happening, which will be after inactive region. So non-blocking assignment. So here the RHS has already taken place in active region, while LHS happens now. So A less than or equal to 0, 0 gets assigned to A. So now when NB update happens, A will be now 0. And also from the previous updates for B, B will be 1, right? So when again I do dollar display here, it prints A is equal to 1, B is equal to 1, because now we have done dollar display happens, it gives A is equal to 1, B is equal to 1. The reason being, dollar display always updates data before non-blocking. So before non-blocking, what is the value of A? It is 1. So before non-blocking, whatever data A has, that with the B value gets updated. So A is equal to 1, B is equal to 1 happens here. A is equal to 0 is not updated in dollar display. You have to take care of that, okay? So then after hash 1 delay, that is now, this was still for T is equal to 0 time, T is equal to 0. Now at T is equal to 1, that is after hash 1, dollar display will print A and B. Now after 1, non-blocking updates are also considered. So A will now be equal to 0 and B will be 1. So the final values of A and B gets updated here. Okay, so you have to take care of these things when you're dealing with the mixture of blocking assignments, non-blocking assignments, and monitor statements in your System Verilog code. Okay, just you can run this on EDA Playground and understand it more better. Let's take one more example. We have here again A and B as two variables, and these are all the three active region assignments happening. So when this gets executed, A will be 1 and B will be 0, correct? Then we have inactive region, $0, which is B is equal to A. So B also gets assigned a value of A, which is 1. So A is 1, B is 1, correct? Then A less than or equal to 0, that is the non-blocking assignment gets simulated. But then dollar display is also there. Dollar display happens in the active region. That is, it will not be taking the updates which happen in non-blocking region. So dollar display will print A is equal to 1, B is equal to 1. So that is in the before the non-blocking region. So the dollar display happens here before the non-blocking region, though wherever it is written, but it gets affected at time 0 because it's written in time 0. It only takes the contents updated before the non-blocking. So we have at time 0, A is equal to 1, B is equal to 1. That is because I have given dollar display. Now, when it comes to dollar strobe, now the feature or the characteristic of dollar strobe is it always displays the value which is at the final update happen to the variables. Okay, the final updates of the variables will get printed. So now that what I mean by this is after non-blocking, A will be 0, right? A will be 0 and B is anyway 1. So this gets printed. That is the final value of the variables A and B get printed by dollar strobe. So we have at time is equal to 0, A is 0, B is 1 for dollar strobe, and A is 1, B is 1 for dollar display, because dollar display considers updates before non-blocking assignments, while dollar strobe updates after all the assignments. Okay, so final assignment only once, final and once, final and once. So displays in the beginning before the non-blocking. Okay, so this is how you can differentiate the simulations and the updates. Example 3, you could see here, I have a module by name display monitor strobe test. Again, we have two variables A and B. In the initial block, A is 0, B is 0. This is in the active region because they are blocking assignments. What is the characteristic of dollar monitor? Dollar monitor gets uh, the print of A and B, whatever is in its syntax, whatever we have included, whatever variables are included in its syntax. So they all get displayed whenever there is a change in the variables included in monitor. So A is 1, there is a change in A from 0 to 1. So dollar monitor gets printed. So dollar monitor prints A is equal to 1, B is equal to 0. Okay, so dollar monitor gets triggered whenever there is a change in any of the input which is included inside it. Okay, so then in the inactive region, B is equal to A happens, so B gets 1. So again, dollar monitor gets triggered. So at time 0, A is 1, B is 1 now. Okay, then non-blocking update happens, A less than or equal to 0. So A again gets triggered, monitor gets again triggered for change in value of A. So it will be A is equal to 0 and B equal to 1 again. So that's for dollar monitor. What about dollar display? Now dollar display executes only once and it updates you the values of the variables before the non-blocking. So before the non-blocking has occurred here. So what dollar display does, it gives the updates of A and B before that, before the non-blocking assignment has happened. That means A is 1 and B is 1. Correct? So that gets displayed. Then we have dollar strobe. Now dollar strobe characteristic, as I said, is it updates the values of the variables at the end of the simulation. That's the final value of the variables. So that's nothing but after all the assignments. So we have A is equal to 0 and B is equal to 1, right? So this is how dollar monitor displays for every change. Correct? And dollar display displays in the beginning. In the beginning. That is before updates before NBA, non-blocking assignment. And dollar strobe, it displays at the end. So that is how these monitor commands work. Let's take one more example here. So we have reg A and B. So two variables again, A and B. And initial begin, A is 1, B is 0. I have taken a diagram here to make things better in a way to understand better. So A is 1 here and B is 0. So it's a blocking assignment. So they take the place of active region, and also dollar display also takes the place of active region. So whatever code which are belonging to blocking or dollar display, they take active queue portion of the queue, right? So A is 1, B is 0, and dollar display gets executed. So we get a value of 1 and 0. Value of A is 1, B is 0. That gets printed on the screen, right? But then actually we have two more assignments here, which are non-blocking assignments. A less than or equal to B and B less than or equal to A. So A gets 0 and B gets 1. So actual swapping happens here. So the final value of A and B will be 0 and 1. But since we have dollar display in our code, and dollar display always occupies the active queue, so it will not reflect the changes which happen in the region of non-blocking assignment, because dollar displays in the beginning, as I said, and it displays contents before NBA, before the non-blocking assignment. The updates which happen to variables, those are displayed. So whatever happens during the non-blocking assignment won't get printed by dollar display. So we have only the updates happening here which gets displayed. So A is equal to 1, B is equal to 0. So we'll not get the updates which happen anytime after that. After non-blocking assignment onwards, will not get. So this is the reason you get the simulation output as A is equal to 1 and B is equal to 0. So this gets displayed by dollar display. Okay. Now, what if I want the final value or to be displayed, or what if I want the value to be displayed every time there is a change in the variable? Then you have to go for dollar monitor or dollar strobe. Okay, dollar monitor, it keeps displaying whenever there is a change, right? So initial begin, A is 1, B is 0. So that happens in the active region. We have monitor here now. Instead of dollar display, we have dollar monitor. So dollar monitor takes the position of postponed queue along with dollar strobe. They occupy this region, dollar strobe, as I showed you all in that picture. So dollar monitor, dollar strobe occupy this region. So A less than or equal to B, B less than or equal to A is simulated. So A will have 0, B will have 1. And now dollar monitor takes charge of displaying the values of A and B, which will now be the values which have been assigned during NBA of the queue, right? So A will be 0 and B will be 1. So that gets displayed in the dollar monitor. Okay, so that's the reason if you want the values to be displayed after NBA, you have to give dollar monitor or dollar strobe. Because dollar monitor is something which keeps displaying whenever there is a change. Dollar strobe is something which displays the values of the variables finally, while in this case, dollar display is something which displays the values of the variables before NBA. So you have to decide which one you want in your code, in your program. So next, let's take this example wherein we have module example 3. We have a 3-bit variable A. So A is a 3-bit variable. And in the initial block, I'm assigning A less than or equal to 3 tick D5. So initially at time 0, A is, these are all non-blocking assignments, right? They are not blocking. So non-blocking assignments. So they take the position here, right? In the third portion of the queue. So in the active region, A is X, the default value. But then A less than or equal to 5 gets executed in the non-blocking assignment queue portion, right? And as soon as there is a change in A, dollar monitor gets triggered. So value of A equal to gets printed. So this is how it gets printed here. So value of A, 101 gets printed. This is what has happened here. Then next non-blocking assignment occurs. A less than or equal to #5 3 tick D0. So at 5, there is a change in A, which is to 0. And since I have a monitor, dollar monitor in my code, so it gets again triggered now because there is one more change in A. So that gets displayed. So value of A is 000 gets displayed. Then the third non-blocking assignment gets simulated, A less than or equal to #10 3 tick D7. So again, A will have a value of 111, so that gets displayed, right? So all the time, because I have dollar monitored here, whenever there is a change in the variable, that gets displayed. Whatever command I have given inside monitor, that gets executed whenever there is a change in the variable which is inside the monitor, which is included inside the monitor. So A is included. So whenever there is a change in A, the dollar monitor syntax whatever command is inside this inside its syntax, that gets executed, simulated, right? So that is how the non-blocking assignments get triggers the monitor and the values get displayed. Let's check this now. For the same previous program, what if I replace $monitor by $display? Now, $display, as I said, occupies the active queue region, right? So active queue region. So whatever happens before the non-blocking, that gets reflected. So what happens before the non-blocking? Before the non-blocking, reg 2 down to 0A. The default value of reg is X. So that gets displayed. So $display will say value of A is X. See, value of A is X, nothing. Later, whatever changes happen to A, because those changes happen in non-blocking assignment region here, my $display cannot see that because $display resides in active region. So whatever changes happen in the non-blocking assignments, $display cannot reflect them. Okay, so if you want all the reflections to be displayed, then you need to put $monitor here. And if you want only the final value to be displayed, you need to put $strobe. And initial value before the non-blocking assignment, then $display. Okay, hope it's clear now. So as I said, that in my picture which I had showed earlier here, I had told that during the non-blocking assignment, updates to the LHS of NBA happens, but also updates to NBAs can re-trigger more active events. That is what I had told. It can re-trigger more active events. So what do you mean by that? So here I have reg A comma B and Y or C. I'm assigning to C A, right? That's continuous assignment I have done. And when I do continuous assignment, C is now sensitive to A. So whenever there is a change in A, C gets affected or C gets updated whenever there is a change in A. So now just see here in initial begin, I have an active region code. I have an active region statement, you could say, which is A is equal to 0. So A gets a value of 0 at time is equal to 0. And then I have a non-blocking assignment. So non-blocking assignment at t is equal to 0 will assign a value 1 to A. So now A gets again updated from 0 to 1, right? So what happens when this happens? See, when non-blocking assignment has triggered a change in A, correct? So this will again, since C is sensitive to A, C gets again changed. Now C was initially 0, and because in non-blocking assignment, A gets updated to 1, and C is sensitive to A, C also gets changed. Whenever there is a change in A, C changes. So C will also get a new value now, which is 1. Okay, so if you now display C after a delay of 1, that is at t is equal to 1, then the updated value of C gets printed. That means C is percentage B comma C, it prints C value as 1. So initially it was 0 and then it has become 1 and that gets printed. Okay, so that is what I meant by saying that whenever non-blocking assignment updates its LHS, then there might be some active region assignments like continuous assignments which may also get updated. Okay, so which we have shown with an example here. Okay, so that's about the different simulation order, the order in which the simulation happens. And we could consider this as a queue wherein active queue, inactive queue, NBA queue, and postponed queue are placed. And they take their simulation orders one by one according to this queue, which I have shown here in the picture. Coming to the next topic, we'll be discussing about clocking, which is one more important feature of System Verilog. So clocking is nothing but a block which is enclosed between clocking and we have an example here which is with end clocking. So that's the syntax, clocking and end clocking. That's the syntax for clocking block. But before understanding what is this block, let's understand something about DUT and the test bench. So here the discussion, I've included knife test bench here. So I'm calling this knife test bench for certain reason. So you can just see that I have written a design which has a logic clock, which is an input clock, then 8-bit data in and 8-bit data out. So that's the port declaration of this particular design under test. Then always at passage of clock, the task which is being carried is data out copies data in. That is, data in is assigned to data out. So that copy happens, right? So in the test bench, wherein I drive this data in at the same edge of data in is driven, and the sampling of the data in is also done at the same clock edge. You could see here, we have the test bench written for this DUT. So you know the syntax and the method how you write the test bench, right? So module TB, then logic clock, logic data in, data out. Then you instantiate this DUT. The name of the module is DUT. So instantiate that DUT, and this is the instance name. And you do all port association by name I have done here. Then you free running clock is generated here with these two statements. So initial clock is 0 and always #5 clock is not clock. So for every 5 clock period, for every 5 clock time unit, the clock toggles on to off to on, right? So here in the test bench, what is being done is always at passage of clock, I'm generating some random value and getting data in assigned to that. See here. So what's happening here is we have always at passage clock in the test bench as well as always at passage clock in the DUT. So there are two different tasks happening at the same time. So in the passage clock, data in is getting assigned with a random value, and also data out is getting assigned to data in same time. Okay, so this will lead to a race around condition, right? See why. On every passage clock, both the DUT is always wants to sample data in. So this is trying to sample data in at passage clock, and the TB is also driving data in. So the TB is driving data in with a random value. But both happen in the same simulation time and in the same simulation region. So that's the active region. It's the region wherein both are happening, right? So the simulator gets to choose which one happens first. We never know which one happens first. Simulator decides which one will happen first. Okay, so that gives you two possible outcomes. What do you mean by that? In other words, you can't predict whether the register in the DUT will see the old or new value of data in, right? So, for example, consider there might be a scenario wherein DUT samples old value. The simulator may run in such a way that this always block executes first, and this always block executes later. See, both execute at the same time theoretically, but practically they cannot happen at the same time. So maybe this executes first and then this executes next. So when this executes first, data out will actually be sampling data in, which is the old data, right? And if this is getting simulated first, then data out samples the new data in, right? We never know what is getting sampled, old data in or new data in. Now this is called as race condition in your test bench versus DUT. And how to overcome this race condition? That is done using what is called as clocking and clocking block. Okay, so thus how a clocking block fixes it. A clocking block is used to manage the timing of inputs and outputs in relation to the clock signal. It specifies when inputs and outputs are sampled or driven relative to a clock edge. And it can also apply skew or what are called as delays to avoid issues like race conditions. Now, how to overcome this race condition? Sampling and driving happening at the same time. How to overcome that? So what we do is we wrap our test bench stimulus, we wrap it with clocking block. So clocking is the syntax, and you give a name to your clocking. So that is CB in this example. And this clocking has to be in sync with some reference. And we generally take clock as the reference. So clocking happens for every passage of the clock here. Okay, so that reference you need to take. And clocking happens every passage of the clock and takes care that there is a skew established with data in. That means you are giving a delay to your data in. So in order to avoid racing condition, right? So data in will be driven for a delay of 1 after the clock edge occurs, after the passage clock occurs. After a delay of 1, you drive data in the test bench, right? And then this is how you do. So now when you, for every clock edge, for passage clock, you want to assign data in with a random value. I have given it as cb.data_in, cb.data_in. That means data_in will be assigned a random value at what value, at not at passage, but after a delay of 1 after the passage. So if my clock was toggling for every 5 time unit, so passage occurs for every 5, then 10, then 15, it's like that. So if the passage occurs for every passage of the clock occurs, so I have a toggling which happens for 5, 5, 5. So my time period is 10, right? So 10, so this occurs at 5. So this will occur at 15 again. This will occur at 25 again, right? So clocking occurs for every passage. So, but my cb.dataIn gets assigned a random value for a skew rate of, for a skew of 1, hash 1. That means if the passage is happening at 5, the assignment to data in happens at 6. If the passage is happening at 15, the assignment to data in happens at 16. The assignment to data in here happens at 26. So you are just delaying it to get assigned for a delay of hash 1. So that is what you're doing. Now, what do I achieve by doing this? Since I'm skewing, I'm giving a delay in to the assignments. Racing doesn't happen here. We avoid racing. Okay. So thus, just to explain what I have told step by step, or whatever I've told till now. So at t, passage of clock occurs, right? So in our case, it is at 5, passage of clock occurs. Then at t plus 1, tb drives data_in. So at t plus 1, because my skew is hash 1. So tb drives at t plus 1 data in. That means it's at 6. Then at t plus delta, DUT samples data in on its own passage blocking update. Okay, so t plus delta, that is the delta region it takes, and DUT samples data in on its own passage blocking update. Okay, now there's a guaranteed 1 unit gap between when the clock ticks and when your TB writes. So the DUT can never collide with your stimulus. So that removes the non-determinism altogether. So what is the meaning of all these statements? Let's see with an example in the next slide. So as we discussed in the previous slide, so this is my DUT, which is at always at passage of clock. Data out is getting copy of data in, right? Now this may lead to race condition, as I said. So what are we doing? We are introducing clocking block, right? So in my test bench module TB, I have declared all the port declarations here, and I'm generating a clock which toggles for every 5 time units. Correct? This is what we are doing. Then I'm also writing a clocking block. So clocking, name of the clocking block is CB, and it is in sync with the passage of clock, which is our main clock, master clock. I'm skewing the data in. So I'm giving a delay to my data in, data_in. By what? What is the delay? Hash 1. So output hash 1. I'm giving output to my data in the clock because data in is driving I mean, the test bench is driving data in. So whichever port is getting driven by the test bench, that becomes the output. Whichever port is getting sampled, that becomes input. So you have to take care of these declarations. Okay. So output #1 data underscore in. So TB drives data in 1 nanosecond after clock edge. That means if post clock edge occurs at 5, then the driving happens at 6. One delay is introduced. Okay, so here in the test bench, then I instantiate the DUT. This is instantiated. Okay, and in the initial block, I'm repeating something for 5 times. What is that? For every passage of clock, whenever there is a passage of clock, I'm assigning a random value to not to data in, but to cb.data underscore in. So what does it do? It assigns the random value, any random value, to data underscore in, not at the clock edge, not at the passage of clock, but after a delay of 1. So not at 5, but at 6. This is getting assigned because I've given skew as #1, right? So then after a delay of 2, I display the data which are stable now, right? Data underscore in, data underscore out. The display, which is the data which are stabilized, get displayed here. Okay. So here, hope you're understanding. So at 5, there's a passage. Then again at 10, there is a passage. Then again at 15, there is a passage, right? So, but data underscore in, cb.data underscore in gets a value at 6, gets a value at 11, gets a value at 16. Okay, so, but then I'm displaying the final changes which happen to data in and data out at #2. That means at 7, I'm displaying at 12, sorry, this should be 15 because it's 10 clock period, right? 5 plus 10, 15. This will be 25. So this happens at 16. This happens at 26. So this happens plus 2. I'm displaying after the clock, passage of clock happens, plus 2 for that. Add plus 2 for that. So 5 plus 2, 7. This is 15 plus 2, 17. This is 25 plus 2, 20, 25 plus 2, 27. So display happens here. So that's what is happening here. So cb.data underscore in equal to $random. Take data in gets random values for every 6, 16, and 26 respectively. But then data out is updated on the next clock edge, right? Data out gets updated at next clock edge in the DUT. Okay, and the display happens at #2. With respect to the passage of the clock, right? So that means plus 2. So 7. So 7, the display happens. So display happens with respect to in and out. What is the in data in value? What is the data out value? So data in is 24 and data out, see, why data out is X here? Because always at passage of clock, data out gets a value of data in. That means this happens at passage, immediately at passage. So immediately at pass edge, the data underscore in is not been assigned any value. Immediately at passage, data underscore in will not get any value. When will it get? It will get at 6, correct? Not at 5. At 6, data underscore in will get a value at 6, not at 5. So data out at 5 will be X because data in is X. Before that, till 5, data in is X, correct? So data out will be X. That is what is getting displayed. So data in becomes 24. That random value gets assigned to data in at 6. At 6, it gets assigned. So that's the reason data out will get that value after in the next clock pulse, that is at 15. So this comes to the data out in the next clock pulse. Whatever data is written at 16, data in, whatever data is written at data in at 16 goes to data out at next clock pulse. So that's what 24 comes to data out in the next clock pulse. 81 comes to data out in the next clock pulse. 9 comes to data out in the next clock pulse. You understood? Because of the delay, #1 delay. So assignments also happen not at the passage, but after a delay. So they get updated in the next passage. Okay. So this is how racing doesn't happen here. So assignments happen without racing. We are very sure that when is the value uh, the data out is getting updated with. We are not confused whether data out gets the old value or the new value. We are very sure that data out is getting the value of data in for every next clock edge. So currently it's assigned a value, and that value gets assigned to data out in the next clock edge, so that we are very sure about it. Okay. So that's about the clocking blocks, which you have to understand, and why to use it, because it avoids sprinkling of delays in your program. So whatever delay you want in your variables to be assigned with, you just combine them, encapsulate them in the clocking block, and then you call the data with the cb dot command, right? The name of the clocking block was cb here. So cb dot variable name, that will automatically embed the delay into those variables. So you need not manually every time specify the delay in your code. Okay. So once you call the data which are embedded in the clocking block, that delay also gets associated, that gets attached to it, and it gets carried to your code. Okay. So sprinkling of the delay is avoided, and by introducing clocking, you can also eliminate the racing condition, right? So the definition of the clocking block is, it's a construct used to define the timing behavior of signals synchronized with the specific clock edge in a test bench. So it always has to be specified with the clock edge, like we did always cb at passage. See here, how did we make it work? How did we trigger it? So we triggered it saying clock CB at pause of it. So it needs something to be in sync with. So we always take the master clock, the passage of the master clock or the neg edge of the master clock. That will be the reference to my clocking. Okay. So that is what we mean when we say a clocking behavior is synchronized with a specific clock edge in a test bench. Syntax is clocking, then the name of the clock, then at of passage of clock, then you mention all the inputs and outputs which need to be skewed, like input signal and output signal, like we did here, right? So whichever signals I wanted to skew, so I wanted input to be skewed by #2, data out to be skewed by #2. So data out is my data out is my sampling. It samples, right? It samples my input. So it should be an input. And data in is something which is driven by the test bench. Data out is sampled and data in is driven. So whichever is driven, that becomes output. Whichever is sampled, the samples, right? Then that becomes the input, right? So you give the skews to those respectively. And then end clocking, you terminate the clocking block with end clocking. The purpose is synchronize the sampling and driving of signals with the clock edge. You need to synchronize, that's the reason. So that will help in eliminating the racing condition. Clocking directions, signals sampled during simulation, they become input. Signals driven to the DOT during simulation, they become output. You have to take care of that, directions of the clocking. So data underscore out was the signal which sampled during simulation. So that became input. Data underscore in was driven, right? It was driven to the DOT during simulation. So that becomes the output. Then timing, signals inside the clocking block are sampled or driven on a specific clock edge, typically passage of clock. What is the advantage? Reducing timing errors in test benches, that means the racing conditions, improves code readability and maintainability. It's clear you don't have to sprinkle delays everywhere manually. You put all the delays inside the clocking block and just call those variables from the clocking block. And they get tagged with the delay and get added in your statement, right? So it's very clear, and readability is there. So that's the advantage. So usage context typically used in test benches. okay, to ensure synchronization. So you can try some more examples, introducing clocking block in your code and understanding how they actually help in order to eliminate racing condition, and also in order to make your program quite clearer and quite readable. They play a very important role. That's it about clocking and about the order of simulations that happen in all these regions of active, inactive, then non-blocking assignments and monitor. Yeah. See you again soon. Thank you.